Okay, I've started recording. Now, if you can't see something or if something else is wrong, just shout. Let me see if I can get this damn thing off the screen. Okay, we're ready to start. I think I should start by reviewing what we said yesterday about Bessel functions. These are called Bessel functions of the first kind because they're the ones that apply when you just have cylindrical symmetry. And as a result, they're kind of complicated. The ones, when you have spherical symmetry, you have the spherical Bessel functions, and because there's more symmetry, they're simpler functions, and they're written with a lowercase j. In any event, they're defined by the Bessel functions of the first kind, capital J sub n, and we start out with n an integer. In fact, we start out with n a non-negative integer, and for n a non-negative integer, the series looks like this. And so that's what we start out with. For small z, the first term is the dominant term. Notice that these converge very well for small z because you have z squared, z to the fourth, and so forth. Moreover, you've got 2n plus 2, 2n plus 2, 2n plus 4. You've got a double factorial here in the denominator. In the sum over m, you've got a double factorial. So these things converge for arbitrary z, an arbitrary complex z, and they converge very rapidly. For small z, the first term is the dominant term. Because the signs alternate, this is minus 1 to the m, the Bessel functions of the first kind have a wave-like behavior. And in fact, for large z, they are a cosine divided by a square root. As I said, they're entire functions, and they obey Bessel's equation, which we saw earlier in chapter 7. Here are plots of Bessel functions, courtesy of MATLAB. The scripts, of course, are in this GitHub. I never know how to pronounce that. I guess it's GitHub because the G in English is normally like that. Anyway, all of them are 0 when rho is 0, except for the 0th one, which is 1. The generating function for these Bessel functions is this magic equation here. I think, this is rather a magical equation. I find all these generating functions to be rather magical equations. It turns out you can take this generating function and derive the series expansion here. And you can also derive the integral representation, which is this integral representation follows from this generating function formula. We may come back to this if we have time, and if you were interested, we could jump back to show how it is that one gets from here to the series expression for the Bessel function and to this interesting integral equation. If you set n equal to 0, this thing simplifies because the n goes away and we get these expressions for J0. and they tell us that for n not equal to 0, Jn of 0, so we'd have a 0 here. Oh, I'm sorry, that's J. Here we've got, well, up here, what we've got is that that Jn of 0 then is just cosine of n theta integrated from 0 to pi. And for n not equal to 0, that's an integral. You see that, in fact, I could show you that if I can get this screen here to display. I can get out a pen. I mean, it's just a question of, let's go to a different color, green maybe. The cosine, of course, from 0 to pi looks like that. So if we just look at, we said z equal to 0 and n equal to 1, the cosine is even. So you can see that the integral from 0 to pi of cosine n of cosine theta, or cosine minus theta, is 0. And for higher values, what you get is that it just occurs more quickly. So what you've got is essentially that. Well, I didn't draw that very well. Here, let me get rid of this maybe and go back to the green, and it looks essentially like that. Well, like that. Anyway, this is pi, and pi over 2. This is for cosine of 2 theta. Again, this is for z equal to 0. This equation for z equal to 0. Anyhow, if you differentiate this generating function with respect to u, then you can identify powers of u, you can get these recursion relations. Then what's more important is that if you take the original formula, this we discussed last time, and express this as a sum over m, you can then relate, remember that, so let's go maybe to red. Remember that z factorial is gamma of z plus 1, and gamma of z is defined for all z except for the 0 and the negative integers. And so in this case, it's z factorial with this definition is defined for everything except the negative integers. So, so defined except at n equals -1, -2, -3, ... And that means then that you can take this expression and for n here, you can just put basically an arbitrary complex number, just as long as you don't cause this factorial to hit a negative integer. And that means that we get that m plus n factorial becomes m plus gamma of m plus nu plus 1. And so this is defined everywhere except when nu is a negative integer. Actually, I'm a little, now that I think about that, I think actually it even is defined for, the gamma isn't defined, but when nu is a negative integer, this sum is such that the divergence of gamma occurs in the denominator, and so we just get zeros. So this J sub nu is defined when nu is a negative integer also, because we just defined it in this way. J of minus n of z is just minus 1 to the n jn of z. So it's still defined. Anyway, so these things are defined everywhere. They're in fact entire functions of z, and I think we've seen now they're defined for all nu. So let me just notice that. The self-adjoint form of Bessel's equation is something we've seen before in 7365 and or whatever the right number is. Anyway, if we set z equal to kx, then it becomes it assumes a form that is more useful for physical problems. What happens here with when you take Bessel's equation and replace x by kx or z by kx, you get a k and a k and a k, so that's 1 over k. You get a 1 over k here, and you have then when you compensate that, you get a k squared up here. If we refer to the general form of a self-adjoint Sturm-Liouville equation, then we see that P of x is this thing, x. K squared is the eigenvalue, and this x here is rho of x. That's a weight function. And we want this to be a self-adjoint system and on an interval, and so we pick typically the interval 0 to b. We could pick, I guess, other intervals and with suitable gymnastics, but the reason why 0 to b is chosen most often is that we have that the jn's vanish at x equal to 0, and p times jn vanishes at x equals 0, even when n is 0. And we need these boundary conditions, and these are the boundary conditions that we require any function v of kx in the domain of the system to satisfy. And we already have that j0 of 0 is 1 and jn of 0 is 0 for all positive integers. And since p of x is x, the terms in this boundary condition vanish at x equals 0 as long as the function, as long as the functions are in the domain. And to make them vanish at x equal to b, we require that jn of kb equal to 0 and that v of kb vanish. And so what does that mean? Well, b is the endpoint of the interval, and that's typically arbitrary. It's set by what the physical problem is. It might be the radius of a drum, surface of a drum, or the radius of a cylindrical waveguide. And so b is fixed, so that means that k becomes fixed because kb has to be a 0 of jn of z in order to satisfy these boundary conditions. So this thing vanishes. This is Zarinsky, remember. And so what we do then is we set k equal to a 0. This znm is the mth 0 of the nth Bessel function. And so these were the British state secrets in the Second World War. Anyway, in terms of them, then Bessel's equation takes this form. B is the physical end of the interval, and ZNM is the mth zero of the nth Bessel function. And so this is the equation that we have. And so now what we see is that the eigenvalues are the ZNM squared over B squared, where B is the endpoint of the interval. And for fixed n, the eigenvalues are different for each positive integer m. And we can see that we can get some idea of what these zeros are when we notice that, where is it? This Jn of z has this form. And so if you want this to vanish, I have to somehow, okay, so if you want that to vanish, what you do is you want cosine of z minus n pi over 2 minus pi over 4 to be 0. So that means that z minus n pi over 2 minus pi over 4 should be what? Well, this is a multiple of pi over 2, but it has to be the right multiple. It's an odd multiple of pi over 2. So it's 2n plus 1 times pi over 2. And so that means that z should be 2n, well, it's actually 3n plus 1 pi over 2 plus pi over 4. So something like that. The important thing, though, is, so this is ZNM. This is the mth zero, the nth Bessel function. And so the point is that ZNM, oh, sorry, hold on. ZNM is something like 3n over 2 times pi, and that goes to infinity as m. Okay, hold on. Where? See. Oh, here's an m. So this is, all right, so I screwed up here. Let's get out the trusty eraser. This thing then is, this is 2m plus n plus pi over 2. And so this goes as, this is going as m pi as m goes to infinity. So this is the completeness relation, that the eigenvalues are going to infinity. And so these Bessel functions are complete. So that's this. And so then if you go back to section 3.38 of chapter 7 and recall the orthogonality relation, that then what we have is our completeness relation looks like this. Well, this is the orthogonality relation, actually, that the weight function is rho, Jn, and for 1m, and so these are different eigenvalues. N represents the system. And so the eigenvalue, the eigenfunctions are orthogonal if the eigenvalues are different. And then the overall normalization turns out to be given by J prime squared sub n. And this turns out to be an exercise. And there are two ways of expressing it. You can either write it as Jn prime squared or Jn plus 1 squared. So these two guys are actually equal. Because they're complete, then the sums of Bessel functions can represent Dirac's delta function on the interval like this. Delta of x minus y is then, remember, this is we can take the weight function to the power alpha at x, and the weight function is just x. So the weight function to the power alpha is x to the alpha, and then we take the weight function at y raised to the power 1 minus alpha. The 2 and the b squared come from here. Those are really the normalization factors. And so we've got the normalization down here, and then these are Jn, comma k, j, n, comma k, where k goes from 1 to infinity, which is summing here. I'm a little puzzled as to why I didn't use m, but so be it. This is the sum. If we set n equal to 1 and b equal to 1, then the sum looks like this. And figure 2, 10.2 gives the plot. Notice that this is 10 to the 4th. We have different scales. This scale is 2 over 1,000. That's the width. 2 divided by 1,000. This scale here is 10 to the 4th. And so the spike is absolutely incredibly thin and incredibly high. The scale of the axes differ by a factor of 10 to the 8th. This is a sum of 100,000 terms of this Bessel function expansion here. And what I did here was choose y equal to a half. So that's I just love these MATLAB expressions for the sum of the delta function sums. Anyway, the expansion of the delta function expresses the completeness of the eigenfunctions. And because we have a delta function like this, then we can write any function f of x like this. And the reason is that we can, if we replace ak in here, what we've got is we've just created the delta function. So normally I write those things in the opposite way, so maybe I should just make that just a little bit clearer. What we've done here is write this as f of x equals x to the alpha, and now we're summing k equals 1 to infinity, but we're also integrating. So let me put that integral here, 0 to b. I'll put a dy out here. And I'm going to put a bracket around this sum. So what goes inside the sum? It's the ak, and ak is 2 over b squared, j squared, n plus 1. This is a normalization factor, znk, the kth zero of the nth Bessel function. And then we have a y to the 1 minus alpha, a jn of zn comma k over b y. And then I'm going to grab the jn of znk x over b. There, I think I can finally close the parentheses. And then the rest of this is the f of y here. Well, we can see that what's in the sum is the delta function. In other words, what's in these square brackets is just 2 over b squared, x to the alpha, y to the 1 minus alpha, and then a sum, k equals 1 to infinity, of jn of nk, y over b, jn, k over b times x, and divided by the z squared n place. So this is actually equal to, once we include the x alpha, that's equal to an integral 0 to b delta of x minus y, f of y, dy, and so that just gives us f of x. So this is a correct equation, and it expresses the completeness. So in other words, because of this delta function relation, we can just express any function in the domain which satisfy, in other words, we need to satisfy the boundary conditions and so forth, and has to be reasonably smooth. Well, I think it has to be, I would say it just has to be continuous. Then we can write f of x as x to the alpha, some akjn of this, where the ak's are given by that. So that's the consequence of the delta function relation. So the delta function represents the completeness of the eigenfunctions. And this is like in quantum mechanics when we have a sum on n equals, I don't know, 1 to infinity or whatever, a state, the inner product of a state and the x position operator and y position operator, and this is then delta of x minus y. And so now we were talking about non-singular self-adjoint systems, so we have a finite interval, and that's the way we normally talk about the Bessel function. But there's an analogous expression for an infinite integral. And for an infinite integral, we have something like this. Delta of x minus y is x times k integral jn of kx, jn of ky dk. And here we have positive values of x and y. And we can generalize these relations from integer n, or integral n, to complex nu with real nu greater than -1. So here's our Bessel function. Now, normally I like to skip some of these examples, but I think maybe in the case of Bessel functions, it's worth maybe going through 2 of these examples. And so I think I'll do that. So let's imagine that we are talking about a drum. And of course, you know what a drum is, so I don't need to describe it. But the potential energy of the membrane is approximately proportional to its area. And when it's displaced, the area is somewhat greater. And if h is the height of the surface of the drum at x and y, in other words, in the z direction, and h sub x and h sub y denote partial derivatives with respect, of course, to x and y, then the extra length of a segment dx is 1 plus h of x. So maybe I should say maybe a word about that. So let's try yellow for a change. So what we've got here is there's an extra length. In other words, the thing looks like this rather than like that. And so what's the difference? Well, this distance is just, what are we calling it? This distance is dx. This distance here is, oh God, what happened? This distance here is h sub x dx, or in other words, it's dh dx dx, which of course is just dh. So that's dH, and this the actual length of the surface here is then square root of dx squared plus dH squared, and that turns out to be square root of 1 plus h sub x squared dx. And you can do the same thing in the y direction. And so the extra area, and it's hard to draw that in 2 dimensions, but you just repeat the square root formula in the y direction, you subtract 1. And then, assuming that the displacements are very small, you get a half h sub x squared plus h sub y squared dx dy. This is actually something that's useful to think about, even though we're not, even if we weren't talking about a drum. So that's or Bessel functions. So that's why it's useful to do this example. Anyway, the kinetic energy, of course, is the square of the speed of the displacement. And so we add in a surface tension term to convert the extra area to N in energy. And we introduce a mass density to convert a squared velocity to an energy. So we have this expression for the action. Action, remember, is kinetic energy minus potential energy for ordinary systems. So we then apply the principle of least action. By the way, the principle of least action is super important in physics. So make sure that you understand the sections in the book about the principle of least action. And here I'm not threatening you with an exam. I'm just saying for your own good, learn that, because it's just super important. You apply the principle of least action to a classical field theory, you get the classical equations of physics. You apply the principle of least action to a path integral, and it then tells you that the classical physics is dominates the path integral, and the quantum physics is the small vibrations, small changes about the classical physics. And of course, when you're talking about very, very small processes, then the small deviations from classical behavior are important. And so quantum effects become important for small processes. Anyway, we minimize the action, so we get the change in, let's see if I can, all right. So the change in the action to first order is 2 h sub t, the change times the change of h of t, and then the same thing for x and y. For the x derivatives and the y derivatives, these are remember, this is the h derivative, the x derivative, the t derivative, the x derivative, the y derivative. And remember that, as we saw many times, the change in the time derivative is the time derivative of the change, and so forth. And so we can integrate by parts. We're dropping the surface term because, in fact, delta H vanishes at the boundary on the surface of the membrane. That's how you make a drum, after all. Anyway, let me see. I really want, I don't know how, I wish somebody would tell me how to keep that guy off the shared screen. Anyhow, what happens then is that we just wind up with the wave equation, namely mu times the second derivative of h is sigma times the Laplacian of h. This is separable, and so we let h be a function of time, a function of space. We get this equation, then after we divide by SV. And then, so that tells us that, well, that tells us that S is a function of T, and this is just a function of X and Y. So we separate, this is that, and this is also that. Omega then is just some parameter that we introduce. These are, of course, the squared frequencies with a minus sign. And then we look at the Helmholtz equation and its eigenvalues. And what we see are the eigenvalues give us the angular frequencies as, in other words, we say here, well, let me unravel this equation because this is a little bit silly here. So what we've got there is that delta V is equal to minus omega squared mu over sigma times V. So the eigenvalues lambda are omega squared mu over sigma, or equivalently, omega squared is sigma lambda over mu, and so omega is square root of sigma lambda over mu. Right. Okay. So the time dependence for S then is this, but the more difficult thing is the height h as a function of position. And we then take Helmholtz's equation, and because we have a two-dimensional disk here, we turn it in, we use polar coordinates on the disk. In other words, surface of the drum looks like this. The radius of the drum is r, distance from the radius is rho, and theta is the angle going this way, theta. And so then Helmholtz's equation, which is actually this equation right here, becomes this 10.26. And we then let V equal to U of R times H of theta, as we know it's separable. We saw that over here back in chapter 7. And so the equation for U then is this, and the theta equation is H double prime over H is minus n squared, so that's the solution here. And now what we're left with here is this is equal to n squared, and that is then Bessel's equation. And the solutions have to vanish when R is equal to RD. Oh, I thought it was rho. No, it is R. So this is RD, and so this is R. And so this, we've got then the self-adjoint Bessel equation, and the eigenfunction then is Jn of ZNM R over RD, because when R is equal to RD, we need to, we get Jn of Z sub Nm, and Jn of ZNM vanishes. And so we satisfy that boundary condition. And our self-adjoint differential equation looks like this. And then the eigenvalue lambda is in this ratio here. And for each n greater than or equal to 0, there are infinitely many zeros. And for each 0, the frequency is this. And so the general solution then is rather complicated. It's the sign for time dependence, another sign for angular dependence, and then the main thing is the Bessel function, Jn of ZNM R over RD, RD being the radius of the drum. Okay. All right, so, oh, hold on. Oh, wow, principle of least action. Okay, well, this let me see if I can just say what it is. What it is that the principle of least action is that you get an equation of motion for a classical theory if you require that the action be stationary. So in other words, first of all, we have something called the action. So this is some integral of something or other. Now, usually this is an integral. In fact, if we go back to this particular case to use this example, the action here is mu over 2 dh dt squared minus sigma over 2 dh dx squared plus dh dy squared dx dy dt. So the action, and in here we've got a Lagrangian. So it's an integral over the surface of the drum and over time. And this is then what we call the action. And what is in classical physics simply magic, or it's a miracle, or the will of God, whatever you want to call it. That magic is that if we set the first order variation of the action equal to 0, then we get the equations of motion. So that's the principle of least action. And if you look in the index of the book, you'll see various places where it's discussed. Various places where it's discussed, and what you then do is what we just did. Namely, we said, well, we want this to be 0 to first order. This thing, what we really mean here, to first order or lowest order in the changes, the change in the time derivative, change in the x derivative, change in the y derivative. And so we expand this just to first order, and then we integrate by parts, we throw away the surface term, and what's left is an equation here that says that there's something in the square brackets time when integrated over the area and over time, in which delta H is arbitrary. So delta H, you see, is arbitrary. So for arbitrary delta H, this has to be 0. But that means that the square bracket has to be 0 identically at every point, every x, y, and t. And in other words, one could have said that delta H is essentially delta of x minus x0, delta y minus y0, delta t minus t0, times some small thing, epsilon, whoops, I don't know why that keeps happening, some small epsilon, and that would give you this square bracket at x0, y0, t0. And so that's the principle of least action. Now, this principle, as I said, in classical physics was simply a miracle, or they called it a principle. In quantum physics, it's a consequence. And the easiest way to see it is to say that the amplitude for something is an integral of e to the I times the action integrated over all processes, so dp, by which you can get from here to there, all processes. And now what's going to happen, of course, is that for most processes that you integrate over, this we divide by h bar. Hold on. H bar is super small. From in fact, in classical physics, it's 0. So we're essentially saying that this is the path integral that gives us this amplitude. This, of course, is Feynman's path integral. Because h is so bloody small, the slightest, all of these things are going to wash out unless S is stationary. So if you have processes here that are neighboring processes and they have almost the same action, then they'll contribute, and they'll contribute the same phase to this amplitude. But if you, on the other hand, have a case, a process, so this will be a classical process. Whereas here, if the action of this process is that, but a not nearby process has a wildly different action, which is the normal case, then another one has another crazy value for the action, then these guys just wash out. This just washes out because you have e to the I s over h bar. And so this thing goes 0 to 2 pi a gazillion times. And so on. So the point is the principle of least action is a consequence of quantum mechanics and quantum field theory, and when re-expressed in terms of path integrals. So that's why the principle of least action and why it gives you why stationary actions give you classical physics. Okay, so that's I think all I should say about that. So let's go back to let's consider Helmholtz's equation then more generally, now that we're finished with the drum. It separates in cylindrical coordinates. We saw that back in section 3 of chapter 7. And that means that if we have minus Laplacian of V equals alpha squared V, then this Laplacian separates in cylindrical coordinates. So we write V as B of rho, phi of phi, and Z of Z. B for Bessel here, and take this and stick it in here, and then it turns out that if B obeys Bessel's equation and phi and Z satisfy these equations, or if B obeys this equation and phi and Z obey this equation, then in the first case we have this, and in the second case we have that. In both cases, n has to be an integer if the whole range of phi from 0 to 2 pi is all physical. When alpha is 0, Helmholtz's equation just reduces to Laplace's equation, and then what happens is the alpha goes away, and so we just have Jn of k squared, or Jn of k rho, or you have Jn of ik rho. And so what we've got then is these simpler equations. And now what we see here is that we have to consider the case where the argument of the Bessel function is real, but also when it's imaginary. And So as a result, I mean, this also happens when alpha is non-zero, because whenever k is greater than alpha, we have an imaginary argument here. Notice that it's either real, the argument of the Bessel function is either real or imaginary, at least if alpha is real. One could have, of course, I guess, alpha complex, and then we would have consider a more general, it would be Jn of a complex argument. Let's leave that aside. We've got enough to deal with here. This thing here is called a modified Bessel function. It turns out that it's proportional to I to the nu, and let's see, I think that nu should be n, actually. So let me just look at 10.38. I think what I should have said was, oh, I'm sorry, there's a nu on J. Okay, so this thing here is real, and it's the modified Bessel function. All right, so, and it's called I sub nu of Kr is I to the minus nu J nu of I Kr. And notice that nu can be complex. So here we have I to the minus nu. That's remember when we talked about complex numbers, when you have a complex exponential, things can get amusing. Okay, this occurs in solutions of the diffusion equation, because in the diffusion equation you see a plus sign on both sides, whereas previously up here we had one minus sign. Remember, as I said to you, the Laplacian is normally a negative operator, so minus Laplacian gives us something positive. And when in fact we have plus Laplacian equals something, then something weird is happening and we need to use a modified Bessel function. So this occurs in solutions of the diffusion equation. And so once again, Laplacian is separable. We write it as B phi z, substitute in here, and we get a solution, both if B obeys Bessel's equation and phi and z are this, or B obeys a different Bessel equation where phi and z satisfy these equations. In the first case, we get we get in of alpha squared minus k squared. In the second case, we get in of alpha squared plus k squared. Notice, you see, what's happening here is that in this case, we have z is e to the I kz, and we get a minus sign. In this case, it's e to the plus or minus kz, and we get a plus sign. Now, if we have this kind of solution, this works if our region in z is limited. If the region in z goes from minus infinity to plus infinity, then this thing is hopelessly huge and non-integrable, certainly not square integrable. I'm going to skip charge near a membrane. If you want, I will do this on Wednesday of next week. It's biophysics, and biophysics is a field that I recommend to everybody. In fact, if people had listened to biophysicists in January, they would have known that the virus was, that coronavirus was transmitted through the air, and all this washing of hands was not irrelevant, but it's the main thing is stay away from crowded places, lots of people, and no ventilation. That's the deadly situation, because the virions just hang in the air for hours. One person breathes, an infected person breathes, everybody else breathes it in, and we're all dead. Okay, so cylindrical waveguides. Took the doctors 6 months to figure that out. Anyway, let's consider, this is an example that's, of course, kind of the defining, the classic or archetypical example of Bessel functions, applications of Bessel functions. So we have an electromagnetic wave traveling in the z direction down a cylindrical waveguide. And what is it going to look like? Well, it's going to look like e to the I n phi, e to the I z, kz minus omega t, and so forth. So where E and B are vectors, and but the z and phi dependence is given by these factors, which are sort of obvious. You've got to be periodic. In other words, you've got, let me maybe shift to a different color. Let's go to red. So what you've got is you've got this waveguide looking like this. And so the angle phi is this way. And so obviously you're going to have e to the I n phi. Z is this way. And so you're going to have e to the I kz minus omega t, where omega is the frequency. So that much is obvious. Because we're just talking about, let's see, where did I, these equations, in other words, what we're saying is that basically minus Laplacian of E is omega squared over c squared E double dot, and minus Laplacian of B is omega squared over c squared B double dot. So these are the equations of electromagnetic waves in vacuum. And what we now have to take account of is that although you have a vacuum inside the waveguide, at least in a simple waveguide, that's what we're talking about. Otherwise, you have some typically non-conducting material, like plastic or something. Anyway, the waveguide, however, is conducting. So this surface here is conducting. And it's, I don't, copper, if you can afford copper. Gold, if you really want a marvelous conductor. Anyhow, so E and B then in cylindrical coordinates are going to depend upon rho. And they can also depend upon, I think they also are depending upon phi, actually. So what do we have? We have certain boundary conditions here, namely that, remember that the boundary conditions are that if you have a perfect conductor, then E parallel is equal to 0, and B perpendicular is equal to 0. So that's what you learn in classical electrodynamics. And so we're going to set E equal to E rho times the unit vector in the rho direction, E phi times the unit vector in the phi direction, E z times the unit vector in the z direction, and so forth. And we imagine the waveguide evacuated, perfectly conducting cylinder, radius r. And so these are the boundary conditions I just mentioned. And so the parallel, the boundary conditions are E in the z direction at r is equal to 0, and E in the phi direction at r equals 0. On the other hand, B in the r direction at r equals 0. So these are the equations that I just wrote down here. Now, if you take Maxwell's equations, you can then derive these equations, and these, of course, are the important equations for a waveguide. And in fact, this is an exercise that I'm assigning for homework, I think, so I don't want to do it for you. you can then, you've got 6 equations here. You can then invert them, and you then get expressions for E rho, E phi in terms of EZ and the rho derivative of BZ, the rho derivative of Z, and so forth. And you get expressions for B's. And E and EZ and BZ are obeying these wave equations. Because of the Z dependence is periodic, and so what you have as solutions of these are that that EZ and BZ then are Jn of this expression here, omega squared over c squared minus k squared times rho EVI NV EVI kz minus omega t. So these 2 factors are the ones that I pointed out in the very beginning here, and the non-trivial part is the Jn. And now, of course, as usual, you have an infinite number of possible solutions, and if you just take some charge and put it in at one end of a perfectly conducting cylinder and shake it, you're going to get all kinds of frequencies on waves, E and B waves, rattling down the waveguide. But and so what you like to do, what engineers do, is focus on some of the simpler ones that they can choose to excite while not exciting the others. And in particular, one choice that's popular is when the Z component of B is 0. So here what we're saying is that, here's the waveguide. We're saying that in here, BZ, which is the magnetic field in the Z direction, vanishes. So this is called transverse magnetic because it means that the magnetic field, B here, is perpendicular to Z. Well, in other words, this is kind of stupid. In other words, B dot Z hat equals 0, or just BZ equals 0. So these are called the TM modes. And now if we can satisfy these boundary conditions and these wave equations, if we choose omega squared over c squared minus k squared r to be a 0 of the Bessel function, and in other words, of the nth Bessel function. So it can be the mth 0 of the nth Bessel function, Zn comma m. And that's because we're writing it this way. So we want this thing to vanish when rho is equal to r being the radius. Remember, this is r, radius of the waveguide. So then the frequencies turn out to be this, because we are saying that this, that omega squared is k squared. So the k squared cancels this k squared, and what's left is z squared sub n m over r squared. R being the radius, of course. It's not a variable, it's a number. And so these are the frequencies of the TM mode. And in particular, the lowest one would be for n equals 0. And the first 0 of the 0th Bessel function is about 2.4. And so the minimum frequency is the speed of light times z01 divided by the radius of the waveguide. And so that 2.4 c over r. So that's for k equals 0. and n equals 0. And if the radius is 1 centimeter, then this is 11 gigahertz, which is a microwave frequency, 2.6 centimeters. And then so for an arbitrary TM wave function, the electric field in the z direction then is given by this expression here. On the other hand, if you set EZ equal to 0, then you're saying that E is transverse, and these are the TE modes, and those boundary conditions are satisfied when this is a 0 now of J prime. And that might be an interesting homework problem. The frequencies then are omega is C times square root of K squared plus Z prime squared NM over R squared. Z prime NM is the nth zero of the first derivative of the nth Bessel function. And Z prime 1, 1 is 1.8. I wonder why I didn't use 0 here. So let me just make a note to myself. Anyway, I chose to examine this one, and the minimum frequency I got was 1.8. And this is lower than that one, and it occurs for n equal to 1 and k equal to 0. If radius is 1 centimeter, then this is 8.8 gigahertz. And so another possibility is a cylindrical cavity. So let me just see how much, yeah, all right, we're just about finished with this section. So I think we have time to do this, at least to do it in a rapid way. Get rid of this damn thing. So now imagine that we take a cylindrical waveguide and we just slap copper discs at both ends. So we now have a perfectly conducting cylindrical cavity that is has just vacuum inside, radius r, height h. And then we get extra boundary conditions because E rho and E phi, you see, let's see, switch to maybe blue. So now we have a cylinder like this. So up at the top, we've got to have E r and E phi equal to 0 in the same, and now BZ equal to 0 because the Z component is perpendicular. So we have these boundary conditions at Z equal to 0 and Z equal to H, the two ends of the cylinder. If L is an integer, and if this is a 0, Z prime NM of J prime N, then the TE fields are these satisfy all the boundary conditions and so forth. The TM modes then look like this. Okay, I think that's that. We haven't had more than one question, so let's see if somebody can ask me to explain something. And I actually have a question. I think we're going to finish the chapter on Bessel functions before the end of the semester. So what do you want to see next? We could do, let me just remind you what the other possibilities are. Some group theory, some relativity, some probability, something about Monte Carlo methods, artificial intelligence, order chaos factor, functional integrals, path integrals, renormalization groups. strings. So, I mean, these are covered in the book. As if you flip through the book, you'll see that I get serious about path integrals and somewhat serious about Monte Carlo method, serious about probability and statistics, and serious about general relativity. Okay, so if somebody wants Monte Carlo, all right, so that's Monte Carlo. We have one vote for Monte Carlo. By the way, Monte Carlo is, all right, we've got group theory, one vote for group theory. I'm surprised nobody said general relativity, in as much as some of you apparently want to do astronomy. And then somebody wants review. So as I was saying, some of you want to do, okay, so somebody said relativity. All right, so we've got one vote for relativity. As I said, relativity, special relativity, of course, is important in electrodynamics. In fact, Einstein discovered special relativity by thinking about electrodynamics. And some of you want to do astronomy, and astronomy intrinsically involves general relativity. In fact, general relativity has become a much better defined subject in the last few years because of these, because knowledge of the universe has improved. It used to be that people doing general relativity would say, well, space is curved and, who knows what's happening. But what we've learned from cosmology is that in the observable universe, space is as flat as possible, or as flat as we can. Experimentally, it's flat. And so the only thing that's weird is that space has been expanding, and that the expansion of space has accelerated with time. So the time dependence and the size of space are both governed by general relativity. And all right, we have a second vote for GR. Right, and also something for forms. Okay. Now the form stuff is more abstract and less often used in physics than the GR. But part of GR is the chapter on general relativity does the part of forms that is used commonly. So there's sort of the easy part of forms and the hard part of forms. And I put the hard part of forms in the forms chapter, and the easy part of forms in special relativity and general relativity. Differential forms, for example, those are nice, and we ought to talk about them if we have time. But as I said, these gravitational waves are real, and they've been detected, and they've provided evidence about black holes. And so black holes, instead of being something that I forget that guy's name, the guy who headed the Manhattan Project in the early 40s. He wrote a paper on black holes, which was one of the early papers on black holes. Guy with the pipe. In fact, that's what killed him. He died in the 60s of throat or lung cancer. Anyway, so black holes are quite real, and seem to be every month or two, we hear that there are even more black holes than we thought. Of course, you have the simple black hole, which is the Schwarzschild solution, but black holes can be spinning, and there are exact solutions for those also. And as far as I know, your most common black hole is spinning. What's rare is the Schwarzschild case. Okay, well, we're just about out of time. What would be useful would be to to talk amongst yourselves to decide what you want to see as a new topic. When it comes to what's important, well, I don't know. I mean, everything's important. I don't know. I'll think about if I can emphasize or review the most important things, but it's a little hard. I mean, we've talked about an awful lot of material, and anyway, I hope some of you will think about taking 467 in the spring, and then we can do a serious job on all of these topics. Of course, the chapter on strings does not by any means cover the subject of strings. And the renormalization group is a short chapter. This is a very short chapter. AI is a very, very short chapter. Monte Carlo methods, that's something everybody should know about, I think. And in fact, evolution is nature's way of doing the Monte Carlo. All right, well, we're out of time, so I'll stop now and say goodbye. And this weekend, try to stay away from crowded, unventilated places, because they are deadly. So goodbye, everybody. I'm gonna stop sharing.
Have a good night. Thank you.
Yeah, you too. Good night. Have a nice weekend. And